Question 14, current flowing in a radio. When it's switched off, obviously that current is going to decay. And that's what we have here. We can see that in our minus power. So the amps in the whatever transistors, the circuits, amps, current decays down at what doesn't actually look like a particularly fast, well, it's in seconds, right? T seconds, fair enough. We have to show that, this is the reason I'm picking this question, because they've left a log in the answer here. I'm thinking there might be some rearranging or little playing around with the log to get the answer. This is quite similar to question 13, which is also a decay question. I talked about how I approached that before when they said we want our current at time t to be 10% of the original current. And I said, well, I'm going to change my labels here a bit. I'm going to say the original current, I'm just going to call that I. Give it some label. We can call it X, whatever you like. And I think, well, what I really want is for this IT to be 1/10 of that. So it allows me to rewrite my formula by saying 1/10 of this initial current, which I've called I, will equal this initial current times this exponential part here, which will start decaying this amount, right? So again, graphically, we're starting at some current and we're decaying down with time, right? Okay. That's it, isn't it? We can start, these i's can cancel out because we know that they're just some particular number, like, I don't know, 5 amps or whatever it is. They're going to cancel out there. I need to unlock this power here using logs. So I'm going to say log both sides of this equation. I get log. Then next step will be to use our log law to pull this power out, times log 2. We might want to rewrite this log. This is log 10 to the minus 1. Because I've got a negative here, and negatives are kind of irritating, I'm going to pull the minus out, minus 10 to the minus 1. I'm going to pull the minus 1 out so that I can cancel those. Now, in the question, okay, I'll write this out. A bit overkill writing this step, but there's a reason why I didn't jump too much. The question had the number 50 in it. It said we had to show that our time was log 2 on 50, I think. And I'm seeing this 0.02, right? What's that? That's 2 1/100ths. What's that? That's 1/50th, and I'm seeing that in the answer. So I think at this point, let's write the 0.02 as 1/50th. We could say at the time, we'll leave it, it's year 12. I don't want to do too many little steps, but in my algebra, but baby steps. So I'll write it like this first. 50, hang on, we're going to get 50 on top. This is wrong. Oh, it's late. It must be this. 50 on log 2. Oh, what am I doing? I can double check that. We've got a t here. Right, see, log 10 is just going to equal 1. That's going to disappear. Let me check the book, see if we're agreeing. Yeah, 50 on log 2. Sorry, my bad. I was trying to go from memory there instead of mathematics. So we've got divide by 50 over here. We need to have t by itself. We're going to have to multiply by 50 both sides. So we get 50 log 10, right? But, you know, what's log in base 10 of 10? It's 1. You should, I think we've done this enough. Of 10 to the power of 1 equals 1. Right? It's saying what power of 10 do I need to get 10? The power of 1. So this time is just 50 on log 2. And this is an applied question. And so let's make sure we put the units in. Now just check, is there anything else to this question? What does it say? Show that it will take 50 on log 2 seconds for the current to drop 10%. No, so we've done that. Okay, thanks.